Okay, chemistry kids, I am just decided to give you another set of practice problems for the redox titration quiz, no, or the titration quiz tomorrow, the lab quiz. So you already have one practice quiz on acid-base titration and redox titration. And so I made another quiz, another set of practice problems that I'm going to walk you through just in case you want more practice with it. The questions are posted in Schoology, and so is the key. And this video will also be there. So hopefully that's, actually doing the labs, which you did, and doing some practice problems with it will help you do well in the quiz tomorrow. So I want to give you just more practice. Some people have asked for more practice, so I made another practice worksheet. I made a key, and so I'm just going to walk you through it. All right. So let's see what the questions look like. And again, it's going to be very similar to the practice quiz that we just did. So let's check that out. All right. So here we have an acid-base titration question. And again, this will be posted in Schoology. And so we want to, we'll read over this and then go through the questions. And then on this side, we have a redox titration question. And yeah, we want to be able to answer those questions. Okay. So let's go to the key and I'll kind of walk you through it. All right. So let's look at this first question. So we have a hydrocyanic acid solution, and in case you didn't know, this is a weak acid, and it tells you right there that it's a weak acid. But you should know that HCN is weak because it's not one of the 7 strong acids that you memorized. And we're told we have a 12 milliliter solution of hydrocyanic acid, and we are titrating it with 0.025 molar sodium hydroxide. So if we try to visualize what's going on here, the HCN is the solution we don't know the molarity of. So this is the solution that goes into our flask. So in this scenario, the person doing the titration took 12 milliliters of the HCN solution and put it in the flask. So we have acid in the flask, and then we are slowly adding sodium hydroxide to it to see how much of the sodium hydroxide, which would be our titrant solution, how much of this solution, which we know the molarity of, is required to react with this much of the HCN. So we could eventually figure out the molarity of HCN, right? We're told that we use phenolphthalein as an indicator. And we're given the initial reading of the burette and the final reading of the burette when the solution turns from clear to pink. So that clear to pink is our indication that we are at the endpoint of the titration, and that's what phenolphthalein does. It's clear in an acidic solution, and then when it hits about a pH of 8-ish or so, it turns pink, and that's our indication. So if we just subtract these, if we subtract 2.51 from 28.84, that'll tell us the volume of NaOH required to react with 12 milliliters of the HCN. All right, so hopefully, that kind of paints the picture of what we're doing. And then let's answer some questions about it. All right, so the first question is just write the net balanced net ionic equation. And we got to be careful here. If it was a strong acid and a strong base like sodium hydroxide, it would be H plus OH minus yields water. But because HCN is a weak acid, you would keep HCN together. And so cyanide doesn't end up canceling out. So you do have one spectator ion. Notice that the sodium is not included in this equation because sodium hydroxide would be disassociated because it's an aqueous salt. So sodium would be disassociated on this side, and technically this would be sodium cyanide over here, but sodium cyanide would be soluble, and so we would dissociate that so that you'd have cyanide ions and you would have sodium ions, so the sodium ions would end up canceling out. So here is our net ionic equation for when we have a weak acid and the strong base, sodium hydroxide. Okay, so hopefully that makes sense to you. And the key is it's a 1-to-1 ratio. And it's because our base has one hydroxide and our acid has one H plus to neutralize, so they're always going to react 1-to-1. Okay. So part B, what is the volume of NaOH required? So that's when we just do final minus initial reading of the burette. So just remember, your burette readings will always have 2 decimal places because the tick marks give us the tenths place and we're allowed to estimate to the hundredths. And when you subtract with laboratory measurements, you're limited by decimal places, not significant figures. So yes, this measurement here has 3 sig figs, but we're subtracting, we're not multiplying or dividing. So we're not worried about sig figs, we're worried about decimal places. So 2 decimal places, 2 decimal places, so we're allowed 2 decimal places. Okay, so it took 26.33 milliliters of the NaOH solution, which has that molarity, to react with 12 milliliters of the HCN. So using that information, we want to calculate the molarity of the HCN solution. So remember, you could use your shortcut MAVA equals MBVB, plug in 12 for the volume of the acid, plug in, 0.025 for the molarity of the base, plug in 26.33 for the volume of the base, and solve for the molarity of the acid. And you'll get this same answer here. But the stoichiometric calculation would be take your liters of the base times the molarity of the base. That will give you moles of hydroxide, and it's a 1-to-1 ratio. So that would give us moles of HCN. And if we want molarity, which is moles per liter, we divide by the volume. And in this case, remember, it was 12 milliliters. So that's 0.012 liters. Okay, and that gives us our molarity. We're allowed 3 sig figs because of the molarity measurement has 3. So that's what we would round our answer to. So you could do capital M here, or you could do moles per liter, or you could write it like this, moles times liters to the -1. It's all the same thing. It's all good either way. All right, so hopefully that makes sense to you. Let's keep going. All right, so now let's answer some other questions about this titration. So this one's just asking us to calculate the pH of the sodium hydroxide solution we used. So remember, if we have a hydroxide salt, we don't know right away what the molarity is of our H plus, but we do know the molarity of OH minus. We would take the molarity of the salt and multiply it by the subscript of hydroxide, which is 1 in this case. So that's 0.025. So we know the molarity of hydroxide. So if we take the negative log of the hydroxide molarity, the hydroxide concentration, that'll give us the POH. So negative log of 0.025 gives us the POH in this case. And then what we would do is we would take that, and it should be, sorry, this is, of course I made a typo on the key. Yeah, this should say 14 minus pH, 14 minus POH, not POH minus 14. Okay, ugh, I disgust myself. All right, so again, this should say 14 minus POH, not POH minus 14. Okay, so when you take the negative log of this and you subtract this from 14, you get this pH. Okay. All right. So that's the pH. That was the pH of our sodium hydroxide solution. Okay. Nothing really to do with the titration. Just kind of a extra little piece of information you should know how to do, and it's just plug and chug in the equation, and that those equations are on your formula sheet, so it's not that big of a deal. You just got to know what it means. All right. And then this question is, why is phenolphthalein the indicator? And it's an indicator which changes color around a pH of 8. Why is this a good indicator to use for this titration? Okay, so remember, in lab, we did a strong acid, strong base titration. And we used bromethymol blue because that changes color, that gives us a green color at a pH of 7. And when you do strong and strong acid, strong base, your equivalence point is always going to be at a pH of 7. And so you want the color to change at the equivalence point, okay? But in this scenario, remember, we're doing a weak acid and a strong base. And whenever you do a weak acid and a strong base, we'll learn how to calculate what the actual pH would be at the equivalence point down the road. But what you need to know is when it's weak acid, strong base, the pH at the equivalence point is going to be above 7. So it's going to be basic. So that's why we want an indicator that changes color at a basic pH, not at neutral, okay? And so you could say, because this titration is a weak acid, strong base titration, we know the pH at the equivalence point will be above 7. So that's where we want our indicator to change color above 7, not at 7. Okay? And part F, this, would never be a question asked on the AP exam, because by the time we take the AP exam, you should know how to calculate the pH of the HCN solution. You would just need to be given a little bit more information, which we'll talk about later. But the reason why we can't calculate the pH of HCN right now is because it's not a strong acid. So if this was HCl, we could calculate the pH of the solution because we calculated the molarity of the solution. And if it was a strong acid, the molarity of the acid solution is the molarity of H+. So if HCN were a strong acid, all we would have to do is take the negative log of our answer from part C, and that would give us our pH, because the molarity of the acid is the molarity of H+ when you're dealing with a strong acid. But we're not, it's a weak acid. So all you need to know right now is if you have a weak acid, the molarity of H+ is not the molarity of the acid. So we know the molarity of the acid, HCN, but we just don't know the molarity of H+, because it doesn't completely dissociate. So really, the molarity of H+ is going to be less than this, but we don't know how much. We don't know how weak of an acid this is. And once we figure out, once we know how to use more information, we'll be able to determine it. But right now we can't, okay? So here we're going to sketch the titration curve. So remember, we get this S-looking curve. We look at the point of inflection. That's the equivalence point. But the key thing I want you to know here is that when we go to the point of inflection, the equivalence point, and we go over here, we don't know exactly what the pH is going to be, but we know it's going to be above 7. So if I mark 7 here, I know that point needs to be above it, because this was a weak acid, strong base combo. Okay, so pH on the y-axis, milliliters of the titrant. In this case, the titrant was the sodium hydroxide, and we're adding base to acid. So at the start of the titration, we have an acidic solution, so low pH, and as we add the NaOH, it starts to increase, and then we get that sharp increase, and then it tails off, and that point of inflection right there, that's our equivalence point. And again, all we need to know about that is right now it's going to be above 7. All right. And then if you wanted to add a little bit more detail, this was the volume of NaOH required to reach the equivalence point. It was the 26.33, our answer to part B, I think, right? Yeah, part B. Okay. All right. So hopefully that helps you out with the acid-base titration. Okay. Now let's go to a redox titration. Okay. So we have a sample of iodine, and they give us the molar mass of iodine. Remember, iodine's diatomic, so it's I2. And they give us the molar mass, so we're probably going to use that so we don't have to waste time calculating it. But it's suspected to be contaminated with inert impurities. So we take a 15-gram sample of this iodine mixture. So this 15 grams is not all iodine. It's 15 grams of iodine and some other stuff. And our goal is to figure out, I guess, if we read forward in the question, what is the percent of iodine in this 15-gram sample? All right, so some of it's iodine, some of it's not. We want to figure out how much of it is iodine, right? And so we take a 15-gram sample of the iodine and we analyze it in an acidic solution with excess amount of sodium hypochlorite. So sodium hypochlorite is this ionic compound. Sodium ions and hyperchlorite ions, okay? And all right, let's start answering the questions. All right, so the first question is just what's the oxidation state of chlorine and that should say hypochlorite. Sorry about that. Okay, so that should say hypochlorite. Well, we would give, so notice that the overall charge is -1 for the whole ion. We would give -2 to oxygen, and that would mean the chlorine in hypochlorite is +1. And again, that should say chlorite. Again, sorry about the typo there. All right. So now this is the reaction that's happening. And we're told it happens in an acidic solution. So we need to balance this reaction in an acidic solution. So the key things here is iodine's going from 0 to +5. So iodine is 0, that's elemental iodine, so 0. And iodine is +5 in the iodate ion. And chlorine is going from +1 to -1. So iodine's being oxidized and the chlorine is being reduced. And so here's like kind of a snapshot of how you balance your reaction. Okay, so again, if you need more review with that, there's a couple videos already posted. You can go check those. All right, but you need to know how to do that. And then the key, I think, to this question, which we'll find out later down here, is we need to know this ratio. 1 to 5 chloride ions. That's the one that we're going to need to know, okay, based on the next piece of information. So 1 mole of iodine reacts for every 5 moles of chloride produced. All right, and so hopefully that's the one ratio that we really need to answer the rest of the question. All right, so follow along. Okay, so the resulting solution, so after all the iodine reacts, the resulting solution, okay, is mixed with excess lead nitrate. Okay, so that all the chloride, that's this ion, all the chloride ions produced will precipitate as lead chloride because it's an insoluble salt. When the precipitate is filtered and dried, we figure out the mass of the precipitate. So this is the mass of lead chloride produced. Okay. So we want to write the net ionic equation that shows the formation of the precipitate. Okay, so lead 2 plus ions plus 2 chloride ions yields PbCl2. Okay. And based on the mass of the precipitate produced, we want to figure out how many moles of chloride were produced. And remember, our source of the chloride, all the chloride was formed by this reaction. So let's, kind of think of what happened. We did this reaction, and to determine how much iodine reacted, we're figuring out how much chloride was produced. And if I know how many moles of chloride are produced, I can multiply by 1 over 5, and that would give me how many moles of iodine reacted, right? Okay. So if we take the mass of the precipitate, divide by the molar mass, which was given to us, that's nice. And then we got to recognize that there's 2 moles of chloride for every 1 mole of PbCl2. Subscript is 2 there. That'll give us moles of chloride. So this is how many moles of chloride were produced from this reaction. Okay. And then based on that, we need to calculate the percent by mass of the iodine in the contaminated sample. So what we would do, we would take our moles of chloride, we would multiply by the mole ratio, 1 to 5. That would tell us how many moles of iodine reacted. We would multiply by the molar mass of iodine. Remember, they gave us that at the top of the question, so we don't have to worry about calculating it. That would give us how many grams of iodine, okay, how many grams of iodine were in the 15-gram sample. And then if we want percent by mass, all we would have to do is divide by the mass of the sample, which is 15 grams, and then multiply by 100. And so we should get around 70.52%. Okay? So hopefully that all makes sense to you and you feel confident for the quiz tomorrow. Just remember a couple typos. That should say hypochlorite, not hypobromite. That should say hypochlorite, like there. And this should really say 14 minus POH, not POH minus 14. Okay? So anyway, hopefully you find that helpful. Have a good one. All right. I'll see you tomorrow for the